All right, this is the first section of our second chapter entitled The Tangent and Velocity Problems. Exciting day for me because we're actually hitting calculus at this point. Everything we did in chapter 1 was just kind of a review of what we did in pre-calc A and pre-calc B last year. So we're going to slowly get in this idea of calculus and being able to take the limit of a function by looking at the tangent and velocity problems today. Let's look at the tangent problem first. I want to remind you what a tangent is from your days back in geometry. A tangent is a curve, or tangent to a curve is a line that touches the curve and has the same direction at the curve at the point of contact. Okay, so just in the open plane right here, suppose this is my curve, the tangent is going to come up and it's going to touch this curve in one place right here. I didn't draw it that well, but it touches the curve in one place, and let's see if I can move it. That looks pretty good. And it's going the same direction. It doesn't go through it, it just touches it in one spot. And so the first application we're going to use of what we're going to learn in calculus is going to be able to figure out what the equation of that line is. So suppose that we have a parabola, and I'm going to purposely draw this without graph paper here, just so you don't get too connected to where it lands at. But suppose we have a parabola, y equals x squared, and I'm going to go to the point 1, 1. Let's just suppose that lands right there. If I draw a tangent line to that point, I'm wondering what the equation of that line is. So we need to find the slope of the tangent line at point P, but we only know one point. And the problem is, whenever we find the slope, we need 2 points. So what we're going to do on this is we're just going to start with a point. Let's see, where do I want to go? I'm just going to go like to right here. Okay, so I'm going to use this black X and this red dot as my point. I'm going to let this black X represent the point 1.5, 2.25. This will help me get an idea of what would be close to the slope. All right. So we said this red dot right here is the point 1, 1. So if I find the slope between these two lines, I am using 2.25 minus 1 over 1.5 minus 1. Now just a general idea of what I did here. I chose this 1.5 at random because it was close to this 1. And to figure out what this function value was going to be, to get this 2.25, I just plugged 1.5 in to my function, and it gave me 1.5 squared, and that's my y value there. Okay. Kind of skip that idea. Whenever I worked this out, I got the slope to be 2.5. Well, that's good and all, but I think I can get this x to be a little bit closer to my dot right there. So maybe if I just get like really close to it, like right there. So now I'm going to say I'm 1.1 on the x-axis. And so that's going to make this point be, let's see, 1.1. Sorry, I closed my parentheses. And if I plug in 1.1 right here, that'll give me the point 1.1, 1.21. So let's find the slope if I was to slide this x even closer to this point. Right. I did that math and I got 2.1. So again, I'm not actually finding the slope of the tangent line. I'm finding the slope. This line is going to be actually just a little bit off. It's going a little bit over to the side, so it's going to be a secant line. I think I can do a little bit better than that. Let me get rid of this last line that I drew. I could probably get a point about right there, really close to that point. I'm going to call it 1.01. That's how close I'm going to be. All right. And so that's going to be at the point 1.01 and then 1.0201 when I square that and plug it into my calculator. So 1.0201 minus 1 So I did all that math, and I get my slope to be 2.01. You know what? I could probably do a little bit better than that. I could get that x even closer. I'm actually going to stop there. I think you can kind of see what's going on, is that I can get these x's to be closer and closer and closer until finally they land right on top of that red dot. Just imagine what's happening to these values. What am I getting close to as I get closer and closer to where that red dot was? Well, my slope's getting closer to 2. And so it's called a limiting value. Okay, I see that my slope's getting closer and closer to 2. The closer that I get these dots right here closer to where the red dot was. And so the way that we would write this, let's see, we would write this as a limit. We'd say the limit, as all these little x's, I'm just going to use the variable x, gets close to 1. So as I got close to 1, I went from 1.5 to 1.1 to 1.01, and then finally to 1. If I took the limit of those into this function where I was finding the slope, it was to equal 2. Now I have something that looks like what we did back in Unit 1. I have a slope. Look up here. I have a point. I can just plug this into my y equals mx plus b. I'm going to change the colors on this so you can kind of see where I'm wrapping this up at. So my slope we said was 2. I'm using the point 1, 1. If I subtract 1 from both sides, I get b is equal to 1. So the equation of that line is going to be 2x minus 1. That makes sense. This red line right here looks like it has a slope of about 2. And with how large I scaled it, it would probably be going through the y-axis at 1. But what I've done is I found the slope of the tangent line, and that tangent line only has one point of contact. So I was able to find the slope of the tangent line using only one point. We can also find the slope of a tangent line from just given data, from empirical data. It wants me to, let's see, this is talking about a camera. The flash unit on a camera operates by storing a charge on a capacitor and releasing it suddenly when the flash is set off. So this is describing the charge Q remaining on the capacitor in something called microcoulombs. I'm guessing that's how you say that. At time t, which is measured in seconds. So first off, it wants me to use the data to draw a graph of this function. Okay, so let's draw a graph of what this is looking like. So let's see, I'm just going to count this by 10 hundredths going this way. So we'll just go 2, 4, 6, 8, 10. Okay, so this would be 0.02. That'll make it easy on me. And then I'm going to put a break in this. And actually, I'm not. I'm going to get rid of that break. Throw it up there. Let's throw it wherever it lands. And I'm going to count by 20s going up. 20, 40, 60, 80, 100, 120. Okay, so if I go through and plot all these points, let's see, I've got 0, 101. That's going to be really close to that 100. 0.02, 86, 20, 40, 60, 86. Again, I'm not doing this on graph paper because close enough is going to be good enough. I'm just wanting to show you guys what's going to happen on this graph. 0.04 and 74, 20, 40, 60, 74. Ooh, yeah, that's close enough. 6 and 63, 20, 40, 60, and 3. See, it's kind of leveling off a little bit. It's not coming down as much. 0.08 and 54, 20, 40, 50. Ooh, my shadow's getting anyway. You can't see my shadow. But I'm working this on my smart board. My shadow's making it so I can't see as well. And then 10 and 47. We'll go 47, maybe a little bit less than halfway. So if I connect these dots, you see that it's following this curve. And what I'm wanting to do is I'm wanting to find the slope of the tangent line at point 4. So this point right here, use a different color than red. At point 4, my tangent line looks something like this. And I'm wanting to estimate the slope of this line. Now on this one, I can't just get closer and closer and closer to it, because if I start throwing my x's, arguably closer to this point, I don't know what value those x's take on exactly, because I'm just given a graph of this. I don't have an explicit function that tells me what the function value would be. So the closest thing I'm going to be able to get to this, to find out what the slope of this blue line is, what color I want to use? I'm going to go to red. Is I'm going to have to just find the slope between these 2 points right here. And so I'll just find the rise and run of those 2 points. Let's see, that's point 2 and point 4. That would be the rise and run of these 2. So if I find the slope between those 2 points, it doesn't really matter which way I go as long as I'm consistent and I head in the same direction. So y2 minus y1 over x2 minus x1. Let's see, I think I worked that out somewhere on here. Maybe not. I have different numbers for some reason. Alright, so I'm going to grab the calculator real quick. A different table than my notes. Didn't catch up on that. So we've got 74.41 minus 86.7. I'm going to divide that by, oh, I'm missing a 0. Were you guys not going to tell me I was missing a 0? Divide that by 0.02, negative 12.31. Okay. Now here's the problem with that answer, is that if I was to connect those 2 lines, if I was to connect those 2 dots, I get a graph that's a little bit steeper than my blue graph. All right, so I probably, if my graph's drawn correctly, I probably overshot the slope just a little bit. It's probably a little bit less than 12. Well, what I can do is, oh, we're running out of colors fast. So what I can do is I can go off this other side right here, and I can do a rise and run off these 2 points. And what that will do is it will give me a line that undershoots it a little bit. So as you can see, the slope of this black line is less than, or it's closer to 0 than the slope of the blue line. So let's figure out what the slope of that black line is going to be. I'm using the points 0.6 and 0.04. So this time it's going to be 63.87 minus 74.41. So let's do y2 minus y1 over x2 minus x1. And I don't have this number ready for you. I apologize, but it is coming up. Divide by 0.02. That's way too big. 63.87 minus 74.41 divided by 0.02. Maybe my last number wasn't big enough. This is negative 527. Let me go back and do this math real quick. I bet you I've divided by 0.2 instead of 0.02. 74.41 minus 86.7 divide by 0.02. Oh. Okay, I guess that makes a little more sense here. If you caught that error, I apologize. So, as you can see, I have the slope of my red line here and the slope of the black line. The reason that they're so big is because I scaled the x and y axis just horribly. I made it so this x axis right here is really small, and I made it so the y axis, I'm covering 100 numbers on this y axis, so it's actually really big. And so I see that my slope is somewhere between this red and the black line. It's this blue line right here. And it's not going to be exactly right, but the best way I'm going to have in order to figure out what that blue line is, my best guess for that is just going to be simply an average of these two slopes. Again, I highly doubt that blue line is perfectly right between it, but it's going to be the best that we're going to be able to do for now. So I subtract off 527, I divide that by 2, and I've got that I landed halfway between these at negative 570.75. And so this would be the slope of that tangent line at this single point right here. All right, this single point, point 4, it only touches the graph one time. So this red line, it ended up touching the graph twice, and then the black line ended up touching the graph twice. And so this blue line will be the tangent line. Okay, let's talk about the velocity problem, and that'll be it for this video. So the other half of this lesson wants me to look at velocity. It's going to be a very similar work to what we did with the tangent lines. But what we're doing is we're dropping a ball from the upper observation deck of the CN Tower in Toronto that's 450 meters above the ground. I think we've done this already, but we're going to be looking for how fast this ball is moving after 5 seconds. You know, I like it better if we just say at 5 seconds. Okay, so we're just going to have to take a snapshot of this ball at 5 seconds and wonder how fast it is moving. Okay. So I'm going to be using my distance equals rate times time formula, except for I'm going to tweak some stuff. I'm going to change my rate, and I'm going to call it velocity, since that's what it's asking for. And I'm going to take it, and I'm going to solve this for v. And so I'm able to calculate the velocity of anything if I just take the distance that it travels and divide it by time. Suppose I'm traveling, say, 60 miles away to Cape Girardeau. If I'm wondering what my velocity was on the trip, I would just take how far it is from Cape Girardeau. I'm not sure what it is. I'm wanting to say it's close to 60 miles if it's not 60. And I would just divide that by how long it took me to get there, and it'd tell me my velocity. Well, I'm wanting to take it a step further. I'm wanting to look at average distance over average time, and that should tell me what the average velocity is. Okay. So if I take the average distance, or maybe even say like the distance traveled, and then I put it over, let me get rid of those averages. Let's just call it distance traveled. That sounds a little bit better. And then instead of average time, let's just call it time elapsed. That actually tells me what the average velocity is going to be. So using the Cape Girardeau example, 60 miles there over the time elapsed. I might not have driven, say, 65 miles an hour all the way there, but that might be my average velocity if I drove for 60 for half the trip on Highway 60, and I got to Interstate 55 and I drove 70 miles per hour on that half of the trip. So my average velocity would turn out to be somewhere close to 65. Okay. Now, one other thing they don't tell me, I'm going to have to go to a physics formula, and I'm going to have to use my formula for distance falling. All right. So distance fallen is going to be given by S of t equals 4.9 t squared, where t is going to be time in seconds, and then s represents the position of this ball that's being dropped off the tower. And again, I'm wondering what's happening right at 5 seconds. So unfortunately, I can't just plug in 5 right here. All right, that's not going to work. Instead, what I'm going to do is I'm going to pick just a time interval to figure this out. If I plug in 5, and this is just going to help me get the distance traveled right here. So if I plug in 5, it's not going to work out. My answer is not going to make sense. Okay. So, but I'm going to do my velocity. I want to pick something close to 5. So normally if you were in class, this is where I would ask you, hey, I would say your name. I say, what's close to 5? And you might say like 5.1. So what I'm going to do is I'm going to find the velocity of this ball between 5 seconds and 5.1 seconds. And so to do that, I'm going to find out where the ball is at 5.1 seconds. So I'm going to plug in 5.1 squared in right here. And I'm going to subtract off. I'm going to take where the ball is at 5 seconds. And just plug that in. And if I divide that by the amount of time that's elapsed from 5.1 seconds to 5 seconds, it will tell me the average velocity. So I've got this to come out to be 49.49 meters per second. Okay. So I took how far the ball traveled from, I don't have these numbers, I don't think, on here anywhere, but how far the ball traveled from where it was at 5.1 seconds to how far the ball traveled to where it was at 5 seconds, and then divided it by the time it took to move there. That told me my velocity. Well, I think I can do a little bit better than that. I can do 5 to maybe 5.01. That would be an even shorter amount of time, and it would better mimic the time that I would be able to estimate as to how fast that ball is moving right at 5 seconds. So using the same idea, I'm going to plug in 5.01 in for its position. So that's where the ball is at 5.01 seconds after I drop it off the CN Tower. And so this 5 right here is going to be the same number this is where it was whenever I dropped it 5 seconds after I dropped it off the CN Tower. And then the amount of time that's elapsed is 1/100th of a second. And whenever I put that in my calculator, I got 49.049 meters per second. I can get closer. I could definitely go 5 to 5.001. And that would give me something closer to 49, but I'm willing to bet that you don't have to go all the way to 5.001. You can kind of see what nice value this is getting close to. Okay? And so we call what we find on this the instantaneous velocity. Because we're finding the ball, the speed of the ball, at one moment in time, at exactly 5 seconds, at one instant. And as you can see, the instantaneous velocity was simply going to be the limiting values of whenever I set this up, whatever value I'm getting close to, that's going to be the instantaneous velocity. Okay? And so these time frames are getting shorter and shorter, all the way down to where I was just using 1/1000th of a second. Whatever that's getting close to, that's telling me what the speed is. So the instantaneous velocity at t equals 5 seconds is, I'm going to denote velocity with the v, 49 meters per second. Again, I never did get 49 meters per second for my answer, but I'm getting closer and closer to it. And that's what we're going to be interested in calculus, is not necessarily what it's equal to, but what am I getting closer and closer to as I approach a really small time interval right here. Here's the set of problems for this section. So you can get started on it and then have some questions ready for me. I'll catch you guys next time.